All right, we're looking at Chapter 8, Section 1, and it's graphing f of x equals ax squared. And that's going to be the more basic, the most basic quadratic function that we can graph. So reading right here, a quadratic function is a nonlinear function that can be written as y equals ax squared plus bx plus c. So this right here is our standard form, and we'll talk more about that later, but that's going to be standard form of a parabola. Down here, let me just read this statement right here. The graph of a quadratic function is a parabola. So I just use the word parabola. That's the graph, but then if you look at the actual just equation, you'd say that he's quadratic. The way that we've talked about this before is with a linear function and a line. Right, so you have something like y equals mx plus b. That's like slope-intercept form that we've used before. That's a linear function, but then when you graph him, he's a line. So you can use those kind of interchangeably, but they are just a little bit different. Right, the line is the picture, and linear is the function. So I said that the graph of quadratic function is a parabola, and parabolas have a U shape. So lines are a straight line. Right? And then a parabola is a U, like the letter U. The quadratic parent is f of x equals x squared. That's the most simple quadratic that we have. The graph of all other quadratic functions can be thought of as transformations of the parent. The point where the parabola changes direction is called the vertex. The vertex will always be the highest or the lowest point on the graph. The vertex of the parent is 0, 0. That's the origin on our graph, the spot where the two axes touch, where the x and the y axis touch. Parabolas have an axis of symmetry. The axis of symmetry passes through the vertex. The axis of symmetry for the parent is x equals 0. And x equals 0 is a vertical line. So what they're saying there is that whenever you graph the parent is f of x equals x squared, which we're going to do in example 0 down here. Whenever you graph the parent, if you also graph the line x equals 0, that's a vertical line, then you could fold your paper on that line, and the left and the right side of your graph would meet up perfectly. So in example 0, let's go ahead and do that. We're going to say f of x equals x squared, and we're going to graph that. So it says graph the parent function and then identify the vertex, the axis of symmetry, the domain, the y-intercept, the x-intercepts, the positive interval, the negative interval, and the end behavior. We're also going to do the range. So beginning graph. Now later on we're not going to use t-charts as much, but right now we don't know what this looks like, or at least you guys don't. So we're going to use x and y. And I'm going to use the numbers -2, -1, 0, 1, and 2. And I'm going to plug those into my function to get the other half of my points. So plugging in for x, I'm going to have -2 squared, that's 4. Oops, that's 4. And then -1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 2. So again, I'm just plugging in to this right here, the x squared. So there's my points. My first point is -2, 4. So I can go ahead and start my graph. And I see that all my y values are 0 or positive. So my graph is going to be more heavy in the top section. Right? So I've got the little bitty bottom section. I have it there just so we can see it, but then the top section is more important. I'm going to put a few tallies on here. -2, 4 is right here. -1, 1 is right there. 0, 0, 1, 1, and then 2, 4. Now we can draw in our curve. I put my arrows on the end, signifying that it could continue on. In the bottom there is a U. Now mine's not very pretty because I can't draw very well. But the bottom is a U. So there's our parent. What we want to do is we want to get that picture in our head. That way when we graph others, we can just use a transformation. And it ends up being a little bit easier than having to do a t-chart every time. So we need to have this picture in our head. It says to identify the vertex. The vertex is the spot where the graph changes direction, and it's happening right there at 0, 0. Next up, I'm going to do the axis of symmetry. If I were to graph in this green line here, that's the line x equals 0. That's my symmetry line. So my symmetry line is x equals 0. Next up, I want to do my domain, and I'm also going to do my range here. Domain and range. So for a domain, whenever we're given a function like this, and it's not like some graph that somebody drew, we're given the function, we're given the equation right there in the beginning, right there. I look for domain restrictions. I look for spots where if I were to try to plug in a number, it wouldn't work out correctly. The things that I'm looking for are square roots, where I can't put a negative under it, and I'm also looking for denominators with a variable in it, because you can't divide by 0. Here, I don't have either of those issues, and there's other ways that we could have issues, but those are the more common ones. Because neither of those situations are here, I don't have any domain restrictions, which means I could plug in anything I wanted. So my domain is going to be all reals. Anything I wanted, I could plug in there. Now my range is not going to be all reals. My range, I look at my graph, and I look to see if there's a bottom of it. So right there, we see that a bottom happens right there at the x-axis. So right there, the shortest spot on my graph, the shortest spot is 0, and that's the y value of my vertex. So all of my y values, all of my range is going to be above or equal to my vertex, so greater than or equal to 0. And if you look over at our t-chart, all of these numbers here, oh, and I made a mistake earlier right there. I put a 2 right there. I am so sorry. That should be a 4. I graphed it as a 4 right here, but I put a 2 there for whatever reason. That's a 4. All right, and I said my y is greater than or equal to 0, and I was saying that all these numbers here, the 4, the 1, the 0, the 1, and the 4, those are all 0 or bigger. So there's my range. Now we look at positive and negative interval. My positive and my negative interval. My positive interval, that's looking for where are the y values positive. And they're positive everywhere except right there at 0, right there at the origin. So for positive, I'm going to say that it's all reals except 0. So all reals given that x is not 0. And then for the negative, I'm going to say, well, there's none, right? Negative would be something that's below my x-axis, something down here. We don't have anything in that situation, so there's none. What else do we need? End behavior. End behavior. Now, there's a couple different ways that we can talk about end behavior. Sometimes we have the more common terms of rises and falls. For end behavior, we want to look at the ends, right? So the arrows. My arrows are both pointing up. So my end behavior on the left, right? We know what the left side of the graph is, right? The left is on the left and the right is on the right. They either rise or they fall. Fall is going to the bottom. So we can say on the left, it rises. And also on the right, it rises. Sometimes we swap these around to say, well, it rises left or it rises right. Those would be good ways to say it. The reason that I wrote the left and right together, or in the first spot, is because I want to show you the fancier way to say it, as x approaches negative infinity. So negative infinity would be as x goes left. Our y values rise, so they go to positive infinity. Then we could say as x goes to positive infinity, this would be as x goes right, so this is left and this is right. Then the y values go to positive infinity again. So with this, we want to kind of think about this little graph here. We got negative infinity, positive infinity, positive infinity. we have our x-axis and our y-axis. Our arrows are pointed like this. So we're saying on the left, he goes to positive infinity. On the left x values, the y values go to positive infinity. And then for the right x values, it also goes to positive infinity. All right. Let's scroll down and look at a different graph. Oh, it wanted did it want our x and y intercepts? It did. I almost forgot. My x-intercept, the spot where it touches my x-axis is at 0. And then my y-intercept, that's also going to be 0. Those aren't always going to be the same spot, but in this one they are. All right, let's look at the next one. Example 1. Identify the vertex, the axis of symmetry, the domain, the y-intercept, the x-intercept, the positive interval, negative interval, and the end behavior. Did it ever say range? It didn't, so we're also going to do the range. So starting off our vertex. Our vertex is a point, and it's going to be that point where it changes direction up there. That's the point 1, 8. And then I'm going to look for my symmetry line. My symmetry line is the spot where I could fold it. It's going to be right there. That's at x equals 1. My domain, similar to last time, I look for restrictions that might occur. There are no restrictions on this one. I look at my equation there. There's no restrictions. So my domain is all reals. Then I look at my range. And my range is not going to be all reals because there are no, for instance, there's no y values up here. Our graph doesn't touch up there. So we have to have a top on our graph. And our top occurs at our vertex. So we're going to say our y values, that's our range, our y values, are less than or equal to 8. Next up, let's do the y-intercept. My y-intercept is where it touches the y-axis, and if I zoom in on this picture, it looks like it happens right there at 6. Now, sometimes we like to list it like just plain old 6, and sometimes it's useful to list him as a point 0, 6. I'm okay with either of them unless I specify. Sometimes on a test or a quiz, it might say, list the y-intercept as a point. If it says that, well, then you need to use a point. Otherwise, you can go either way. The x-intercept, this time we're going to have 2 of them. One right there at -1, and then one at 3. So we have 2, -1, and 3. And again, you can list them just numerically like that, or you could list the point -1, 0, and the point 3, 0. Either way is okay, unless it's specifically stated. Next up, we want to do positive interval and negative interval. So we got positive and negative. Now on our last graph, it was kind of easy because everything was positive except just one little bitty spot. This one's not going to be quite as convenient. We have these x-intercepts here, which means that in the middle we have positive because it's arched above the x-axis. Then these edges, it's negative. So we describe the positive and negative regions using the x values. So my positive region first, I'm going to use an inequality. I'm going to say that our graph is positive between -1 and 3. So I'm going to say -1 less than x less than 3. And then for negative, I'm going to say it's for x is less than -1 and for x is greater than 3. Now this covers my whole number line except for my x-intercepts, right? I never used a less than or equal to symbol or a greater than or equal to symbol, right? I never had the equal to because right up here I have the -1 and the 3. Those are my actual x-intercepts. Those are zeros, right? You've probably heard that x-intercepts could be called zeros. So zeros are different than positive or negative. All right, let's scroll down. In behavior. Now I'm going to write it using the infinities. So I'm going to say as x goes to -infinity, y goes to, and then my other one is as x goes to positive infinity, y goes to. So you have this little template that we can follow. This means as x goes to the left, y goes, and our arrow's pointed down, so negative infinity. And then as x goes to the right, y goes again, negative infinity. Now, if we want to, we could combine these. You don't have to do this, but you can. You could say as x goes to positive or negative infinity, y goes to negative infinity. And that lets you write it together. You can do that if you want. You don't have to, either way. But there we are. All right, next up. Ooh, before I forget, I want to highlight a few things here. Our x value, that 1 on our vertex, is also listed right here in our symmetry. Those are the same 1. And then I want to highlight the 8 for our y value. We have an 8 down here. Though that is the same 8, or those are the same 8s. They're used together. All right, that's it. Now, for graphing ax squared, we already graphed just plain old x squared, but now we want to graph ax squared. And a, right up front, that is our stretch or shrink factor. So we've probably seen something like g of x equals a times f of x. And that a in the front stretches or shrinks, or it could reflect our graph. Right here we have some rules. When a is positive, the parabola opens up. So that's like our parent. A was positive, a was 1, so it opened up. When a is negative, the parabola opens down. When 0 is less than a is less than 1. So when a is less than 1 and bigger than 0, there's a vertical shrink. You know what? Let me put a little absolute value there because I think that would make it work better. If the positive version of a is between 0 and 1, it's going to be a shrink. And then whenever the absolute value of a is bigger than 1, the graph's going to be a vertical stretch. And I'm going to do an example of that right here. We're going to graph g of x equals 1/2 x squared. So our a equals 1/2. 1/2, that's going to be a vertical shrink. So we're going to have a vertical shrink by 1/2. So we have now described the transformation. That's what we did right there. And now we need to graph. So I'm going to graph the parent first, and then we'll graph our new graph. So I'm going to say that I'm going to graph right here. Let me see if I can make my graph just a little bit bigger. So f of x is x squared. And we might remember we had the point 0, 0, 1, 1, negative 1, 1, and then the points positive and negative 2, and then up 4. The thing that I want us to get from here is that these first 2 points are 1 unit above our vertex. And then our next 2 points, our next 2 points are 4 units above our vertex. This number 1 and 4 is going to be really useful because in our graph that we're about to do, we have a vertical shrink. So the verticalness is half of what it should be. So let's graph g of x equals 1/2 x squared. And I'm going to do this without a t-chart. So my origin, my vertex is still at 0, 0. And then my next points, I'm going to look at my 1 and my 4, and I'm going to multiply them by our a factor, so 1/2. So we get a 1/2 and a 2. So this means that our first points are going to be a 1/2 unit above our vertex. So they're going to be left and right 1, and then a 1/2 above. And then our next 2 points are going to be 2 units above, and then left and right 2. And now I can draw in my curve. My curve is a little bit wider than the parent because we had a vertical shrink, so that makes it wider. We see that the verticalness of this guy, if you took the distance there, is a half, whereas the distance there is 1. The distance here is 2, whereas the distance here was 4. The left to rightness, there's probably a better way to say that, is the same for both of these graphs, but the verticalness got halved. All right, let's look at example 3. So this one has a 4 hanging out front, so that's going to be a vertical stretch by 4. I'm going to really quickly graph my parent. This is f of x equals x squared. Okay, and on our first homework assignment, on this homework assignment, we want to be graphing our parent for every single problem, because we really want to make sure that we have this graph just stuck in our head. The numbers 1 and 4 were used on the parent, but this time we stretch by 4. So our numbers are going to be 4 and 16. So now when we graph, my origin is still the same, my vertex is still the same. I'm going to go left and right 1, and then instead of going up 1, I'm going to go up 4. 1, 2, 3, 4. Oops. Now the 16 is going to go way off my graph, so I'm not going to worry about that. I'm just going to graph those 3 points there. This is g of x equals 4x squared. Alright, let me find a problem with a negative hanging out front. I don't really want to do number 4. You guys can do number 4 on your own. Number 5, let's do it. The negative hanging out front is going to be a reflection in the x-axis. And the 5 is going to be a vertical stretch by 5. So our graph, this is our first one where our graph is going to be facing down. So again, let me graph my parent. This is going to be f of x equals x squared. And then to the right of him, I'll graph my new graph. This is called HH. H of x, I guess I need probably more in the bottom there. H of x is negative 5x squared. So again, my verticalness of the my verticalness or horizontalness of the vertex doesn't change. He stays at 0. But then I use my numbers 1 and 4, and this time I multiply by negative 5. And I get negative 5 and negative 20. So my first set of points are going to be down 5, and then left and right 1 unit. And then my next ones, if I wanted to do that, would be down 20. I'm not going to graph the ones that are down 20 because I'd go way off my graph. And there we go. That's going to be h of x equals negative 5x squared. Just something to make note of because this is our first one. We now have a maximum on our graph. Our maximum is right there. It's our vertex. And our range here would be y is less than or equal to 0 because it's below our vertex there. Alright, there we are. That is the first section of chapter 8. Next up, we get to do when we move the graph up or down.